Yesterday, I showed some motivations about why caring about causality constraints, positivity constraints, because they give you an orthogonal direction in trying to build the parameterized low energy physics, in addition to the user requirements, understanding what degrees of freedom you have, which symmetries you have, and today we are going to dive a little bit more in details through examples, which I think are some paradigmatic examples that teach you some general lessons. So let me start with one example, which is the one U1 Goldstone boson that you get from breaking a U1 global symmetry spontaneously. And you write the Fati theory for this, in this case. So you write, so you have a Goldstone boson pi, which is invariant under shift symmetry. So you write down all terms allowed by the symmetry. So the kinetic term is certainly allowed. So it's good. The theory of particles. You normalize it this way. The next term that you get is this one. So d pi squared, meaning d mu pi, everything squared, divided by some scale, and some coefficient I'm going to call C2. It's our normalization. And then you can keep going, okay? Then the next term will be something like this. D pi squared box pi, m cube, it's a normalization C3. And then you can have d pi and so on to suitable powers, to 8, and so on and so forth. So, and I want to show you that there is causality will force C2 to be positive. And moreover, so this first goal, show you how causality can be used to determine this, which is completely, from the point of view of symmetries, is that C2 is undetermined. Moreover, I want to show you when C2 is much smaller than C3, which you perhaps want to fine tune, or use symmetries to claim that situation. They show you that is going to be inconsistent. So not only C2 must be positive, must be larger than C3. And that's where we are going. Let's try it. So the idea is to, if you have C2 on the wrong side, you are able to build some background solutions of the equations of motion upon which perturbation can travel superluminally. So let's see. So what are the equations of motion here? So you get, so you vary the action, you get derivative of minus d mu pi 1 plus d pi square over m to the 4th C2. And then corrections. Then C3 m cube d mu pi box pi minus box d pi square over 2. That's all. Equals 0. So a solution of these equations of motion is the following. So is you take d mu pi constant, so some constant vector. Okay, so the solution, in some regional space, in this case very large, you are deep inside, you are neglecting what happened at the boundary, breaks Lorentz spontaneously. So there's some bulk of matter here that, being there breaks Lorentz this way. For example, this happens, for example, in inflation. Okay, you have a scalar field pointing. We have pi dot constant in some direction. And this corresponds to pi equal to a constant plus this x mu. It happens also in for superfluids, for example, it's also a solution. And if you wanna, so let's focus on this case first. So where we are neglecting higher derivative corrections. So let's focus first on this part. And this is gonna be a good approximation as long as V mu squared over m to the fourth is going to be much smaller than 1, right? Because this is nothing but d pi square over m to the fourth on the background. So let me call it the background. I'm going to call it with a bar. This is just saying that this term is going to be smaller than this term, so other terms are even much smaller. And moreover, we're going to require that dd pi is also small. In this case, it's constant, so it's actually 0. Don't even need to specify that small. It's as small as it can possibly be. So, and further derivatives as well. So under this condition, we can truncate to the leading part of the interaction. So we're going to focus first on this part here and look at the solutions around the background. Now we look for pi equal the background solution, this one, the pi bar is this, and then mu pi bar is this. We look for a perturbation around the solution. So we plug the perturbation here. So can this produce a linear term in phi in the perturbation? So my Lagrangian for the perturbation will be the Lagrangian. I started with pi bar plus phi, then I'm going to expand in phi. So it's going to contain L phi. Then what's next? What's the first term? Can it be linear in phi? What? Quadratic. Why quadratic? Because the equations of motion. Because we solved the equations of motion. So the first term is going to be 1/2 d phi square plus C2 over 2m to the fourth d phi square v square. So v is the vector, is this v, okay? Plus 2 d mu phi squared. Okay, this is the first term. Then there could be some eigenorder. We're looking at small perturbation, so we can truncate. We can truncate to this order. So this can be also, well, there is also the terms from the eigenderivative, which I'm also not putting. So this is also the same as, it's better written this way. So you see that because we're breaking Lorentz spontaneously, the kinetic term here breaks Lorentz spontaneously. This term can be dropped here because by assumption it's more. Okay? We're working in effective field theory assumption, so that's not important. Term is not going to beat. It's never going to beat the one he has next to it, so we can drop it. So you see that the kinetic term here is the standard one, plus a correction given by this direction of this. So the equations of motion, in particular for the perturbations, will look like this. So you see that there is an effective metric, just that there is flat space metric, Minkowski metric, that's corrected by the background. The presence that this perturbation, these wiggles on the background are traveling on a background. Okay? So if you plug here plane waves. These are linear equations, so you can expand in plane waves. You get the dispersion relation now looks like this. It's k squared plus 2 C2 and to the fourth V dot k square equals 0. And if you draw the light cone for this case, this will be the Minkowski light cone. Now you actually get broader as soon as C2 is positive, is negative. C2 negative, the light cone gets broader, it opens up. So now this perturbation can travel also in this region here. One way to see it explicitly is writing down the effective metric here, more concrete example. So this is the inverse metric with the up indices. So if you write it, so the effective metric with lower indices is going to be eta mu nu minus 2 C2 m to the fourth v mu v nu. And let's take just, I mean, this is a true fact, you can check it. If when this is negative, you're broadening the light cone, but I want to do it, explicitly. So let's take v mu time-like. For example, let's take the d mu pi bar is some number, which is units of mass square, in the time, for example, pointing in the time direction. Okay. So pi is basically pi bar, basically some constant times alpha m squared times t. So in this case, this metric here is just minus 2c2 and to the fourth alpha delta mu 0 delta mu 0. So you can draw it as a matrix. So you get 1 minus 2 alpha c2. Sorry, there is a m square is gone. Then you get 0, 0, minus 1, minus 1, minus 1. Right? So the null geodesic for this metric you're traveling into is going to be dt squared 1 minus 2 alpha c2 minus dx squared equals 0. So your speed is going to be dx over dt squared, right? It's going to be 1 minus 2 alpha 2. Sorry, I forgot the. No, it's good. Like this, alpha 2 c2. There's a c2, importantly. Alpha squared, sorry. Alpha squared here. Squared is important because it's v and the square here, so this alpha gets squared, such I cannot flip the sign. So you see that indeed, if C2 is positive, you travel a lower speed than 1. If instead is negative, you travel superluminal, as I was saying here. If C2 is negative, you broaden your cone. Instead, if C2 is positive, you go inside. So in general, a more covariant expression here for the variation of the speed is just minus 2 C2 mu square over m to the fourth for a time like V. Exercise for the audience, repeat for a space like V, see what's going to happen. So I will come back to this point. So you're saying, well, you travel superluminate. Then what? That's what you're saying, right? So what's the problem? So if it was in a Minkowski space, would already be a problem, right? If it was in Minkowski space, I would not need to run any further argument, right? If I can travel here, I can then have a system where I travel as well here. Then I can send a message here and go and close a contour. I'm coming to that, so not in this language, not expressed in terms of propagators. I will show you that you can form closed time-like curves, so which is an inconsistency because you thought you sent a signal, instead you didn't, you prevented. Okay, so that's I'm going to show you this. For the moment, I'm just taking traveling superluminary as a proxy for a causality issue. Okay, just bear with me, so we'll get there. Okay. So in flat spacetime, well, we will see. So we'll see how it happens. Now we are no longer in flat spacetime. We have in a curved spacetime, not curved. Sorry, in a spontaneously broken spacetime. So where there's no Minkowski, and so we'll see how the picture changes. So basically, this is the first thing I wanted to do is this. So maybe so you can have perturbations. Travel luminally if C2 is negative. So that's the first thing I wanted to show you. So now, second thing. So indeed, even though the symmetry would allow you either sign, if you don't want to travel superluminally, have in mind that you're going to form closed time-like curves, then you have to require that C2 has to be positive. Now, if let's move to the second point here. I want to show that C2 cannot be suppressed either. So the second point, I want to show that C3 cannot be much larger than C2. Even though, for example, you have a Galilean symmetry that would allow you to do so, or you can think perhaps you will fine-tune that. There is no. You're going to see that also in that case, you can always find a background solution where you're going to travel superluminal. So let's take first the case where we take C2 very, very small, 0, and we focus on as C3 to be in the first leading term, and then there is the rest. In this case, we want to find that you're going to travel superluminal perturbation around a certain background. In this case, the equations of motion will look like this. And a simple solution of this is when pi gets some value, some function pi bar, which is a traveling wave. You get in particular some function traveling speed of light in some direction. You can see, for example, that so box is 0, the mu pi bar square is 0, so it's going to solve. It's going to solve, and dd pi is also 0. So all these terms are separately 0. So this is a solution, is a traveling wave in some direction with speed 1. And we apply the same logic. We are going to perturb around it. So take this solution. We look for the equations of motion for the perturbations. So in this case, you get the Lagrangian for the perturbation. Looks like this. So there is the normal one that you get C3 or n cube. So you need to put one background insertion and two perturbation insertion. So one is this one, where you put the background here, but box pi is 0, so this term is going to vanish. And the other one is when you put one background here, one perturbation here, another perturbation here. So you have two choices. You get minus C3 d mu pi bar, d mu phi box phi. Okay, so that as equations of motion. For the perturbation, you get minus box phi plus C3 m cube. Let's write it this way. Eta mu plus 2C3. First of all, maybe I have to tell you what the expectations are even before doing the calculation. You see, before we had d pi to the fourth, to get the quadratic part, I had to insert twice the background. So it was quadratic in the background. Here instead, since this is cubic, to be quadratic in the perturbation, the background is going to be linear. So it's kind of obvious. If this propagates subluminally, I just flip the sign of the background. It's going to propagate superluminally, so it's kind of obvious that I don't need to do much. But unless, there's an exception, unless when it travels always linearly. In that case, flipping the sign doesn't do anything. That's why I have to do a little bit calculation here. And so let's look at a solution of this type for the perturbation. So let's look for another traveling wave with speed v. So let's look at a solution of this type in the same direction of the background solution. Okay, so let's plug this here. So phi 0 is a function of this, so it's a traveling wave, it's speed v. So let's plug it here, so we get an equation for v. So this is going to give us phi 0 double second derivative of this function times v squared minus 1, which comes from this part. So v equal 1 or minus 1 would be the solution. You can travel either way with speed 1, I mean on the cone. And then there's a correction from the part that breaks Lorentz spontaneously, which is 2c3 m cube d nu pi bar. No, what am I writing? 2c3 m cube pi 0 second derivative v plus 1 squared equals 0. So there is a non-trivial solution. So if this wasn't there, the solution would be v equal 1. This one is there. There's another solution, which is v equal 1 minus 2c3 over m cube pi 0 second prime 1 plus 2c3 m cube pi 0 second prime. And you see that whatever the sign of C3, so regardless of the sign of C3, I can always choose pi 0 here, such that pi 0 second times C3 gives you a velocity here, a speed bigger than 1. So regardless So the variation of V here, which is minus 4 C3 over M cubed 0, can be either ways, regardless of the sign of C3. So whatever C3, so as long as we can neglect C2, which was the assumption, as long as C2 can be neglected, for example, by asymmetry, pi 0 here is the solution of the traveling wave for the background. So, yeah, maybe it's a bit misleading. So pi is a function of t and x. So I found a solution, I call it pi background of t of x. And that itself is a function of a single variable, function of pi 0 of this single variable. So you see that C3 will always, you can always find a background, whatever sign, choose a sign, there's always a background from which will travel the light cone broadens. So you can propagate outside the light cone. Can it be an approximate symmetry? So this cannot be an exact symmetry, that's what we just established. So can it be an approximate symmetry? So let's add back C2. Let's turn on C2 and see let's see when C2 saves the day. So if you turn on C2, your equations of motion, which are here, so it gets modified. You get eta mu, this term, and then you get a correction from C2. So you can repeat, you can plug in your ansatz for the solution for the perturbation in this case, and see that it will change this equation a little bit. There's a correction due to C2, and the solution is nothing but adding here -2. So in order to always get positive regardless of what this is doing, you need that this one beats this one. But that's precisely the condition. That's precisely the condition that this one gets beaten by this one. So it's never a good symmetry. So as long as you require this is always more than 1, then C3 never dominates. Questions so far? Yes. Well, this is pi 0 prime squared. So if C2 is positive, as we established, has to be. Yes. So let's neglect this. So well, if you say it's larger. So you mean I can find a pi 0 second such a complex? Well, I'm going there. I'm going there. So I'm gonna show an example. So let's see. Let's see an example. So yeah, it's a very good point. So let's try the following. Let's try to have this one dominate. By the way, what matters is not too much C3 versus C2, but it's really C3 times you see, is C3 times this part and C2 times this part. Who is winning? So the pies are there anyway, so you have to count them. But let's run the following question. So we are in effective theory. So even if you travel a little bit outside the light cone, perhaps it's not a big deal because you have a finite resolution on the time advance you can create, right? So for example, so if this is the Minkowski light cone, if I travel a little bit outside for a certain time, so a certain distance here, and I arrive earlier than if I had traveled luminally, I get some time advance, arrive earlier by some delta t advance. If this one, I cannot resolve it, so it's actually, suppose it's comparable to the resolution I have with the effective theory. This way, I would assign it to the fact I'm done a mistake because I truncated eigen derivative terms. So the point really is whether I can make it parametrically much larger. And you can. So if you take m delta t advance, you can ask yourself how big can it be? So let's run this exercise. So let's take, for example, pi 0, which is dominating. Let's take a region where this one is such that pi 0 is roughly constant. So let's take pi 0 second here. So roughly constant over a region L. Since here I have pi 0 prime, so it means that pi 0 prime grows. So the pi 0 prime goes like, schematically, it goes like this at the boundary of this region where I created this background solution. So this one can win over this, but not for arbitrarily long distances, right? Because I could try to, even if I have a tiny deviation from luminality here, I could imagine, well, I travel longer, I make it bigger. Except that if you travel longer, this guy eventually wins over this guy, right? Which is the very notion of being less irrelevant than this one. A long distance, the less irrelevant dominates. Of course, it's expected. So as soon as you go to long distance, you learn nothing. So you cannot go too much so you cannot push this L too much. So how much? And then we will see how big this can be, or that maximal L we can hope for. So let's take, so delta V3, so the one coming from C3, this part. So we said is scales like C3, so I'm dropping all factors of 1, C3 by 0 second over m cube, and delta V2 instead is C2 by 0 prime over m to the 4th. So in this one, we said scales like C2 by 0 second times L, square here, squared over m to the 4th. So now I want to ask that I can travel superluminally for as much as I can possibly sustain. So I'm going to demand that delta V3 is dominating delta V2. This is going to give you an upper bound on L. Eventually, L gets larger, so it violates this. So L, well, you solve for this equation, you get Lm squared, it must be less than C3 over C2, m cube over 0 second. Okay, so this is the maximum length you can travel in units of the cutoff. Okay, let's plug this maximal length you can travel. You dot it with the velocity, which is dominating, to get how much time advance you're going to get. So you get m times time advance is nothing but m times L times delta V3. ML is this one. So this is going to be bounded by the square root of that. And then have delta V3, which is that expression. Then you put all factors in a nice form. And this is C3, C2, M cube. So you see that as soon as C3, basically as soon as C2 is smaller relative to C3, this one can be very large. And so you can get that M, you can make this one parametrically large. And this one, make it, for example, C3 order 1, C2 10 to the minus 2, then you get this much larger than 1. So you can resolve the difference. You can see that this difference cannot be ascribed to neglecting higher derivative terms. And so it's really not an error due to the truncation in the effective theory, but we are really building something that you would notice, that you would trust it. Okay, now when I come back to the question was raised about why should I care about going superluminary in the first place? So it's because you can run into contradictions if you don't. If you're not careful, this one I can erase. Mm-hmm. So there's a bit of a so I wouldn't so the background must be in a certain sense nice, right? Because if you build pathological backgrounds, well, but it's not quite enough, right? Because you can build solutions of equations of motion in GR which are totally crazy, and you discard them, white holes, right? Solutions. So that's exactly one of the limitations of this method. You have to have another rationale behind that's selecting which background is a good background or not. This example is traveling plane waves, so I think it's very much trustworthy. And moreover, it's going to be confirmed by the amplitudes positivity analysis. But I'm saying that you need to be sure that you're not, the pathological you're seeing is in the solution rather than in the Lagrangian you started. Not all solutions are equally good. Just as if you look at solutions which have negative energies, not good. So I'm presenting this argument because I think is instructive, but it has its limitation. One of the limitations is this. Although it has also some strengths relative, so maybe I should anticipate. So we are going to move at some point to discussing similar bounds using scattering amplitudes, which in a sense are more powerful because don't run in these, you have to be careful that your background wasn't crazy. And they give you sharper bounds. Here you see I was using a lot of wiggles, right? So I said C3 cannot dominate, but how precisely can be 10 times perhaps okay, 5 times, 100 times. So this is not very quantitative. So instead with positivity of the amplitude, you get a sharp C3 is at the most 5.4. So very informative. However, there is no bound on positivity, to my knowledge, coming, for example, for higher points in the Lagrange. Instead with the backgrounds, you can bound. So you see there's a trade-off on the method. We will see them. So let's try to build a time machine. When delta V is bigger than 1. So let's see it. So the strategy is the following. So you have you form a background. It's a regional space-time, and under certain conditions, you have shown that you can travel outside the Minkowski light cone. You can send a signal here. Okay. Is this a problem or not? So let's try to build a closed time light curve. Now, the argument in Minkowski space, you can no longer use it, because if you boost it, you're changing the background. It's not Minkowski, you boost it, boosts are isometry, so Minkowski goes in Minkowski, still analysis applies. Here, no, you broke spontaneously Minkowski. So let's have for example, another blob somewhere which is boosted relative to this one. By the way, you can, of course, I'm going to assume that you can send signals in either directions. Also in this way, I'm going to need that you can send in all directions, or not in all, but in the opposite direction, you'll be able to send, which is not obvious. Of course, if you're breaking a background, perhaps it's a preferred direction. Okay, so I'm going to assume that this is possible. If I can send a superluminal signal in this way, in this direction, I will be able to send it also in that direction. So let's now, so this is a blob basically localized in the plane Tx. This is a third axis here. Let's put another blob here. Let's moving with some relative speed relative to this one, which is boosted. So projected, so it's here, is in this plane here. Projected on this plane, it will look like this. This is the light cone. Okay, it will look like this. And you can send, because it's boosted, you can send signals now back in time. So you have a Lorentz contraction that deforms the blob relative to this one, which is a rest, and you can send signals here. Okay. So let's try the following. So you send a signal from here to here, and this takes some time. So let's call this point 1. This point 1. Sorry, from here, so you send it, this one, for example, has 0, 0. Now, you send it to point 2. And point 2 is going to have, so minus t, then vt, the velocity I'm traveling. Okay. So this is first step. Now you exit the blob, you go in the transverse direction, right? And there you travel luminally. You are outside the blob. So you go to point 3. Point 3, which coordinates. So let's imagine that from this blob and the other blob, there's a distance impact parameter, the scattering with the impact parameter b. So you travel some time b to get there in the transverse direction. Minus t plus b. So projected, so you're traveling in the transverse direction, so projected in this plane, you're traveling, looks like you're doing this. You are at rest for x here, so not changing, you're moving time here. So projected on this plane, it looks like you're doing this, up to some point 3. Okay. There, you encounter the new blob, for which you can propagate superluminally back in the other direction. So you can, right? So you can go. So this will take some time, t prime. You get, so I want to get at in the same direction s, so I travel for a time vt, so these are going to get 0 here. So for a space vt, and 0 b, I'm going to require that I'm at a distance b, minus b. So, for example, the v prime here, the velocity I need to do this is going to be the distance I want to travel, which is vt, divided by the time, which is given here by t minus 2b. So it's actually slightly larger than v. It is slightly larger. In modulus, larger. So it's also superluminal. You see it here also from the drawing. The slope is more than this slope here. Well, now you're in business. Now you can close, because now you can go back from this blob here. So you boosted, travel here, boosted back. Now you're traveling back to the same point here. And so to this point. And since you're traveling in the transverse direction, it looks like this. You're reaching in a time b, you're reaching exactly 0, 0. So you remove, traveling with the opposite direction removes this b. This is minus b by the t prime chosen for a suitable velocity. So I get back to the original point. So precisely, you can form this type of sort of contradiction. You can send a signal such that prevents you to send the signal. It doesn't make any sense. Unless you're Christopher Nolan. Questions? So to come back maybe to the question, whether it's front velocity, doesn't matter. So as long as you can be able to form closed lifetime curves, so that's a relevant point. Questions? Otherwise, we move to photons. So this is a concrete realization of what I promised yesterday. Symmetries are good, but not quite good enough, right? So C2 negative is allowed by symmetries. C3 larger than C2 is allowed by symmetries. But they are not good enough because they are missing some extra information. So we need to pay attention to something more, some extra ingredients. So there are no questions. I move to photons. Yes? C3 positive or negative. Either ways, doesn't matter. You can, because it's cubic, so you can flip the background. You can. The sign of C3 is totally irrelevant. You cannot fix it by changing the sign. Indeed, this is confirmed by, we will see it by the positivity amplitude. C3 can actually be negative, can actually be positive, but cannot be large, can never be dominate over C2. Well, that's what I would define as causality condition. You are able to form contradiction because there's no notion of, yeah, of course, I mean, so you shoot or you are being shot by yourself. Who was the cause of what? So that's the. So how much time I have? 10 minutes? Okay, that sounds great. Okay, let's look now more interesting, well, I don't know if it's more interesting, another concrete example, stereo photons, where the deep IR, where you have no other charged particle in particular. So the leading term is a quadratic term in the field strength, and the next two leading, there are two of them. One is this. There is another one, which I'm not going to write to simplify the calculations. So, but there's going to be an exercise for you. So actually, I prepared some exercise in case I can maybe put it on the website. So that I invite you to try to solve. Okay? So it's very instructive. To try to do it yourself. So for simplicity of the argument, let's focus on the case where I have this leading operator and neglecting the other one for simplicity. So the equations of motion, and of course the dot also are higher derivative terms, which I'm assuming, I'm in the standard, and the assumption that these are the leading. Okay, let's start with a simple case first. And moreover, if I go to sufficiently long distance, unless this is exactly 0, but if it's not 0, if I go to sufficiently long distance, this is always going to dominate, okay? Regardless of the size of the other. Let's put ourselves in that limit. So the equations of motion will look like this. So an obvious background solution is F mu constant, right? Constant. This is an example where you can definitely trust the solution, right? This is a constant magnetic field pointing in some direction. Right? We believe this is a good solution since Maxwell, or a constant electric field pointing in some direction. Or, yeah, that's two examples. And expand around that. So you get the background solution, then the fluctuations. And you plug here, and you get the Lagrangian for the fluctuations. Looks like this. F rho sigma, F bar mu. Well, let's write this way. So it doesn't, it's very similar. I mean, it's quadratic, so can it be possibly very different than before than this case? It's very similar, right? So you have a quadratic term as usual that will allow you to propagate perturbation superluminally on the background. But this correction of the background here gives you some twist on various directions. Now it's a slightly more complicated problem because now you have the polarizations, right? So the photon has two polarizations. So you can perhaps propagate superluminally one, but not the other, for example. So you have to be careful. So in order to analyze this problem, so this I leave to you as an exercise. So repeat what we have done for the scalars to this case and determine that A must be positive in order to avoid superluminal propagation of little f. So that's the exercise. And perhaps if you want to challenge yourself, you can add also the other one. Maybe I give you a hint. So yeah, so you can turn on a magnetic field or an electric field, or can even change background a little bit. Another one would be you take E dot B 0, for example, with E same size than B. So as a background, you can try to build a solution. And so you have to play a little bit around. I wanna cheat a little bit. So let me do it here on the blackboard in the remaining 5 minutes. A simplified version of this. So this is in 4 dimensions. Let me discuss in 3 dimensions, which is much simpler. 3 dimensions is much simpler. Why is it much simpler? You know? Do you know how many polarization has the photon in 3 dimensions? 1. It's a scalar theory, in fact. So this is dual. It's actually in three dimensions. This is dual. A scalar actually to a Golson theory. So, and okay, maybe let me just say it. You map this literally to this theory. So This theory is dual to the following. What is it? Okay, let me write it here. It's going to be dual in 3 dimensions. So in 3 dimensions, d pi squared as dimension 3, so dimension 6, this squared. So besides, sorry, 3. Besides this, it maps to this with the same A. So the A that you see there is this A. So, but we ran the argument before, we didn't care about which, how many dimensions we were. So, from the previous calculation, right? So, let me show you the duality, which is interesting on its own. It's not part of the topic, but it's cool, and you see, allows you to solve problem in one shot. So let me maybe show it for general knowledge. So the point is the following: that you want to try to, so you have this constraint, df equals 0, means that f is dA, right? That's, we write f is a 2 form. You build from a 1 form, right? Because you have this constraint, which is one of the Maxwell equations. Now, in 3 dimensions, this reads like this. So it's epsilon mu rho d rho f nu rho equals 0. Okay. So let's impose it as a path integral condition as a delta function on the path integral. So let's integrate over f rather than a, but with the constraint that it must be the d of a dA. So delta function of that condition. Right? So whatever path integral you were doing it, you can write it this way, the integrate over dA. It's going to be equivalent. But now you Fourier transform the delta function. So this one is going to be integral over d pi e to the I pi epsilon mu rho d mu rho. So you're adding, so whatever Lagrangian you had here, that you're integrating over all points of space-time, over whatever Lagrangian you had, you can think of it rather than integrating over A, you're integrating over F with a new Lagrangian. So it's minus F mu nu squared plus F mu nu to the 4th A over M to the 4th, in this case 3, because we have 3 dimensions, sample factor, and then plus pi epsilon mu nu rho d f nu rho. That's a totally nice result because you see there is I can integrate this by parts, put this derivative here, and now f comes with no derivative, so these equations of motion are a constraint. I can solve the constraint and plug it back in the action. So f is going to be proportional to 1 plus a over 2m cubed 1/4 epsilon, no, 1/2. Well, so there's a number here, mu rho d rho pi squared. So of course, the duality is totally, super well known. The standard case for Maxwell, where you have just one. But you can extend it to any Euler-Heisenberg type of theories, or Eiger dimensional version of it. You're adding Eiger derivative terms. You see, they appear like this. You plug this back here. This was is an algebraic equation that so you get the equations of motion. It's an algebraic equation for f. This is a solution. Plug it back, and you land precisely in this one. Well, but I can define it this way, right? I can define, who told you that your path integral was the correct one to start with? And saying, this is the path integral, e to the f, integrating all f subject to the constraint. That's perfectly well-defined path integral for the gauge field, right? So I think it's a detail that doesn't matter. That's why I didn't pay attention to writing it. Because I can start directly with that as a definition of my theory of gauge. Sorry, say it again. No, I'm summing over field configurations subject to these constraints. This is right. This defines a gauge theory, a Maxwell theory in 3D. Okay, I think I can stop here. Questions? So I have so for maybe to tell you what's coming next. So next time we will discuss an example with gravity, and then we will move to discussing positivity through amplitudes. And see so I will first drawing the connection explicitly. How come the subluminality gets translated to positivity? So we're gonna go through in detail, and then apply it in concrete examples. Questions? Yes. Dimension 4. This on this, for example, for dimension. Not that I'm aware of. Well, in a sense, it would be surprising. I mean, to me, it would be surprising because. So let me put it this way: as long as you're writing all terms of dimension 4, you know that you're writing basically a normalizable theory. So that's theory. You know basically that's a theory with a very large cutoff. Seeing a pathology there. No, but sorry, I take it back. Yes, I have an example. Sorry. I have an example. Indeed, when is an example of this type, where the pathology you see it at time advance due to the presence of the Landau pole. So the Landau pole may not be physical, but there's an example which I actually worked on. So I don't know why I forgot. But take QED coupled to gravity, and with the cutoff of QED much below. Let's say with the Landau pole of QED much below M Planck, which so is not our word QED, but you can change the coupling QED. So you lower the Landau pole below M Planck. So in that case, you can see that you can get a time advance. So that's an interesting question. So you can calculate. So you have photons here, loop of electrons. So you're really doing a calculation, a normalizable theory for what matters for what concerns QED. Then the inconsistency comes when you couple it to gravity. So it is a graviton here. Here you couple it to something else. This type of diagram is going to give you a time advance unless your physics comes earlier than the Landau pole. So in a sense, causality constraints is telling you, look, there is a Landau pole somewhere. So even though if you didn't need to study, for example, suppose you forgot, so you didn't know that the beta function is positive in QED. You knew already that the coupling gets strong, a shorter distance. Well, you would discover there is a upper bound, there's a strong coupling limit in this theory by looking at causality. It's not really what you were asking, because it's not really only dimension 4 operator, because I'm coupling to gravity, which is an irrelevant operator. So you see it through coupling through gravity. In fact, the proportionality factor is proportional to the beta function. So it's the sign of the beta function that I show you see it here. But yeah, That's the only example I'm aware of. But you discover something you knew already. There was a pathology to begin with in the theory you were aware of. So it was the presence of the coupling getting larger. Something has to break down. Something new states or a new description on a strong coupling must come in. You cannot keep the same. So in F or in derivatives? In which variable? Derivatives of F? So for positive bound from amplitudes up to 4 Fs, but arbitrary number of derivatives. You can catch them all. All of them you can say something about. 4 Fs only, so 2 to 2 scattering. Statement about 2 to 2 scattering. Instead with the background method, I think you can catch more, but I haven't tried. Perhaps it would be interesting. Maybe try first a simpler example with scalars. Yeah, for something what? Non-locality, meaning no, but within the FTT, the non-locality is never resolvable. It's never resolvable. I'm probing distances which are larger than there would be no locality, 1 over m. I never see that. I mean, the no locality you're talking about is this. You integrate out this guy, yeah, so you know about another point in space-time which is elsewhere. But it's due because you're propagating a degree of freedom from here to here. At low energy, it looks like this, that's correction, but you never resolve it. You can never claim it, right? Because you're going to distances which are larger than 1 over m, because you are in the FTT. So you can never claim you see a no locality. So you would maybe let me add. You would notice if you would allow yourself to go past m. In a sense, yes, you do see a no locality, but you understand it. It's a propagation of a particle from one point to another point. Like this one you call it local, because the interaction of that particle and themselves happens up to a point. So indeed, you propagate from one point to another, but in a controlled way. Yeah, you have a question? Mm-hmm. Mm-hmm. Yeah. Well, C2 is not, right? C2 doesn't run. The leading operator never runs, right? C2. So d pi square, C2, d pi to the fourth, m to the fourth, plus higher terms. So let's try to do a loop. C2 here, C2 there, m to the fourth, n to the fourth, bunch of derivatives here. So you get C2 square, 16 pi square, m to the 8. So it's going to be d pi with suitable power. Not going to normalize. It's not going to normalize this one. Right? So this one doesn't run. Ah, okay. So it's a different question. Okay. Yeah. Can I defer the answer to the? So I prepared a lecture where there's a discussion about it. So we'll be worth more. So let me put it this way. So the constraints are not going to get. It's not going to be on decoupling. So yeah, maybe, so an example here would be on, I add the next, let's say D4, for example. Let me add the C4 here. I think this one, yeah, this one is C4. We normalize C4 here, which is this one, so 3, 12 minus 8, 4. Yeah, so this is C4, is this one. So C4, we will see, also has to be positive at 3 level. Now you're asking, what about loops? And now C4 gets normalized by C2. However, by dimensional analysis, you will see that the effect on C4 is going to be that the positivity is going to be on the rounding coupling. And the strongest bound is going to be a C4 at the matching scale, M. That's going to be the strongest constraint. Below that, so is that satisfied, or lower energies automatically satisfied by unitarity? That unitarity will imply that if it's satisfied on the running coupling at the matching scale, it's satisfied to all longer distances. This is for C4. For the other one, let's say C6, the story is different. So, but I'm going to tell, so I don't want to have that lecture now in the last couple of minutes. Yeah. So at 3 level, so you can also say, the general lesson is that you're going to have infinitely many constraints, but they're not going to be on a coupling at a time. They're going to be on a combinations of coupling. So you see, for example, rather than having C4, so C4 positive would be the positivity bound at 3 level. Now instead you're going to get something like this. You're going to get C4 plus C2 square, 16 pi square, some number that you have to calculate, log E over M has to be positive. And the sign here is such that this is important, E over M. But you see, if you're in perturbation theory, if your coupling is, if you can do perturbation theory, this one is never gonna flip the sign of C4 by being in perturbation theory. The loop correction is gonna be small relative to the 3 level. If your theory is strongly coupled, if this is order 1, then it's a different story. Well, so I would claim that what we are doing is that, because the amplitude, so but is on the polynomial growth. So the amplitude, remember I was saying that C2 control E to the 4th. So it runs very quickly with energy with E to the 4th. And see, can it run faster? Can the amplitude run faster? Can you be dominated by this one? No. So I was thinking that it puts you bound on the polynomial running of the couplings. Now you're asking more. You're saying, can it put bounds also on the quantum effects due to the running? Okay, I think for the leading or for the next, for the first few, let's say C4, it tells you this. It tells you that, it tells you something. It tells you basically it's going to fix this coefficient to have a certain sign. It's kind of trivial. You knew it anyway. No. So if it's positive, no. So you know that at the matching scale, you saw that it has to be positive. Then automatically, by unitarity, you know that a lower scale must be also positive. So you learn that it has a definite sign, the beta function. You learn that this number has a definite sign. The beta function has a definite sign. But it's kind of obvious. In this case, it's obvious. It's a square. Discontinuity. So this is a square. So it teaches you something, but something that you knew. You're doing this. Basically, you will see that you can calculate this from this special relation. The special relation integrates discontinuity, but discontinuity is a squared, so the running is positive. Okay.